Okay, so in this recording, this doesn't class, I'm going to repeat some of the things which I missed out in the previous recording. So there will be some amount of repeat, but there will be also new ideas and some slides which I had to correct because they were not consistent with the IJ, with the notation. So those things I have corrected. So what we already discussed in the next class, that's in the previous recording, is that suppose there was an element of fluid here where the fluid was at this point suppose was flowing in this direction. So there's an amount of fluid and this is a fluid element. It is flowing in this direction and thereby it has momentum component in the x direction and in the y direction. And suppose some different element of fluid was flowing out through the surface in this direction, and again it has component in the say x direction as well as y direction, whereas the surface through which it was flowing out or is flowing out is pointing in this direction. In the n is this is the surface normal, this is the surface area, this is the surface normal, hence this is the direction of the outward normal to the surface. And as the fluid which is basically uh, pointing in this direction, the surface normal is pointing in this direction through which the fluid is going out through this direction. As a consequence, we can say that x momentum is passing through this surface in the y direction, because as the fluid passes out, you could say that momentum in the x direction is passing out in the y. eh, X amount of momentum or momentum in the x direction is flowing in the y direction, and that essentially is uh, captured through this term, where if you take here x amount of momentum, if you take one component of it, is flowing in the x direction, in the y direction, and in the z direction. And this of course is a tensor, um, right? And if you write, so basically you can say that the change of momentum in volume v, so this is the momentum in volume v and rate of change of momentum at a certain element in space, that is equal to the flux of momentum. This is the flux, this is the momentum, this controls the flux of momentum through the surface, and you have a u dot ds, right? Because you could talk about momentum flowing out in the y direction, so n dot ds, right? So and ui is the momentum which is flowing out, so correspondingly just think about it, it's rho u into u dot ds, and this is the body force per unit volume, right? Because we are writing everything in per unit volume in terms of the density. So that's the body force per unit volume, and this in turn can be written as this, on taking the dot product you have nj uj, and if you convert it by the Gauss's divergence theorem, um, from a surface integral to a volume integral, then you will get correspond to this nj surface area, you will get a divergence of j um, into volume. So there should be a dv here, so there's a dv here which I missed out here, right? And so this was already in terms of volume element. Now if you're talking about the same volume element, the volume element is not flowing, it's fixed in space at the moment, so you are looking at del t, right? So this is the general equation which holds for the compressible flow as well as incompressible flow, right? uh, but but if you talk about incompressible flow, and I remind you that you can have incompressible flow divergence u equal to 0 even in a compressible fluid, as long as Mach number is less than zero point 0.3 or zero point 0.1, right? So Mach number has to be low. And so what I've written is not incompressible fluid, but incompressible flow. Then, as I've shown previously from the conservation of mass equation, the divergence u equal to 0 holds. And then this equation can be simplified, and as I will show you in the next slide, uh, as in which case you can take the rho outside del del t, because density is not changing as a function of time in the flow. And then you can write this as del del t of ui, if you write integral over the volume, right? And if you make this operate over these quantities and rho is a constant, then you will get uj del del xj, right? Because the other term, as you will see, when you get divergence, yeah, so we'll see in the next term, then basically we'll get a term like this, and this holds only for the incompressible fluid, because we incompressible flow, because we have used this equation to drop some terms. Let's see how was this. So this expression is exactly the same as this expression. And for simplicity, for aid of visualization, think of I equal to x. So you're really talking about the x component of the momentum, right? You're talking about the x component of the momentum, and now you are taking a derivative with respect to time. And here we have not yet assumed its incompressible flow. So hence you get, when this del del t operates, it can operate on del rho del t as well as on ui separately. So that's what has happened. Here you have del rho del t dux and rho del ux del t. Integral over dv del del x, and I've kept the rho here so that you see that it's inside still. And so del del xj, and there's a repeated index, which when you break it out can be written in terms of del del x, ux, del del y, ux, del del z, uz, I mean ux, and rho is still inside, and fx into dv. Now, since we're talking about the same volume element, uh, I've removed the integral sign here, and then this equation becomes something like this. So where you basically what I've done is make this operate, uh, make this operate over ux, make this operate over uy, and keeping ux outside. So I've kept those two different terms, right? So the equation now has, this gives two terms and this gives six terms, and on the right hand side you have fx, which is force density, force per unit volume. And if it is incompressible, then you can take these rho out, and then divergence u equal to 0, so these terms will drop out, right? Moreover, since rho is incompressible, this will also, you can take it out of del del y and del del x and del del z. So basically, this operating on rho, which is a constant of a space and time. So even this will drop out. And if it is incompressible flow, then you will get a simpler equation, which is rho del u del t plus rho u dot diverge grad. So this is an operator acting on u, uh, equal to force density. And you also have divergence u equal to 0, which denotes incompressible flow. So this equation denotes how the momentum or the flow field is changing as a function of time. On the other hand, as we shall see in the next recording, when there is no time dependence, then we can also use divergence u equal to 0 if it's a steady flow and solve certain class of flow problems. including with obstacle and so on and so forth. Just give me a moment. Yeah, so this comes every 10 minutes into the call. So yeah, so you get this simplified version, which is applicable only if the conditions are such that the flow is incompressible. If you have to use the compressible, if you are dealing with compressible flows, then you have to use this equation, where you have many more terms, as you see. But this can be simplified if you have incompressible flow. So for the incompressible flow, I have written down Euler equation without viscous terms. Euler equation is without viscous terms, and that's applicable for a class of flows. Actually, even yeah. And so then you get this equation, right? Now, this total body force, which is on the right hand side of the equation, uh, can be broken up into two terms. One which is acting on each. So suppose this is a fluid. This is an amount of fluid which has different fluid elements, and one is a body force, where something like gravitational field, which is acting on every element of the fluid, and the other can be quantities like the pressure, which act only at the surface. So on this amount of fluid, it acts only at the surface. So this fluid exerts some pressure on the outside fluid. On the other hand, the outside fluid exerts some force. Pressure is nothing but force per unit area. So exerts some force uh, normal to the surface at every point on the fluid. So this fluid exerts some force in this direction, this exerts some force in this direction, and so on and so forth. So this total force density can be written down into pressure with a minus sign, and the minus sign is the reason is the force being acted on at the surface is due to the pressure of the fluid outside, which is acting inwards, which is opposite in direction to the outward normal. Hence, you have a minus p sign, and this is the body force. And this surface integral, if you convert into a volume integral by the Gauss's divergence theorem, then you get grad p, right, a derivative, and the minus sign remains, right? So as a consequence, you have um, Euler equation. This is the standard form of the Euler equation without viscous terms for incompressible flows, and for compressible flows, I've already told you. Uh, you have this equation per unit volume. There should be a row here, right, for matching units and so on and so forth. So it's because, yeah, this has, yeah, so this is not dimensionally massed. There has to be a row here and there has to be a row here. And now you can solve this equation for URT and pressure. There are four equations here, and there's one equation here. You can solve for that for incompressible flows. Note, I'm not mentioning the word fluid, it's flows. And as I discussed, that you don't need the energy equation, because if it's an uncompressible flow, then PV equal to nRT. I mean, if the density doesn't change during the flow, in course of the flow, the velocity changes, but the density doesn't change. Then for ideal gases, you could use PV equal to nRT, and for non-ideal gases, you would have more complicated equations like the van der Waals equation. Now, for ideal gases, I can remind you that the pressure depends essentially on temperature or the velocity distribution of the velocity, the equilibrium velocity distribution. I mean, this holds only for equilibrium. right? P equal to nRT, because these quantities like temperature and pressure are defined in regions close to microscopic equilibrium. Uh, yeah. Mhm. Uh, well, if gas is in flow, right? So you assume that within that you have a small enough fluid element within which there are enough collisions, right? So that you can talk about the thermodynamic temperature of that element. So the number of collisions and relaxation to equilibrium for that volume element is much faster than the rate of flow, right? So locally, for units of time, which is much larger than the microscopic time, you can define quantities like the pressure and the temperature. And if you have non-ideal gases, if you have liquids, then there will be interaction, and pressure will have not only a kinetic term or a um, microscopic velocity dependent term, where pressure depends upon the microscopic velocity of each of the atoms and molecules which constitute the fluid, but also will have a contribution from uh, the interaction and you can look up the virial coefficient. It's also called the Irving Kirkwood formula. So that's the microscopic definition of uh, flows, right? The other point to note is that for if you have compressible flows, you would also need the energy equation to solve for density as a function of x, y, and t. You will have more variables. uh, the other thing to I would like to comment here is, suppose you had no external force, there was no gradient in pressure, then you could write this equation, the Euler equation, as rho uy, right, which is the momentum, the rate of change of momentum, um, and divergence of current, right? Where now you have momentum current. Now you have momentum current here. So divergence of J. So this looks really like this. Now this quantity here, so this was a scalar, and hence you had a vector here. Now the thing which is changing itself is a vector. So you could have three components of momentum which is flowing out in different directions. X can flow out in X direction, X momentum in the of I mean X component of momentum can flow out also in the Y direction, ways that I showed before. And hence, instead of having a current, this quantity is a tensor. So if you had, uh, so if this was written in the matrix form, then the first row, the top row, if you like, would be rho into ux. That would be the first element. The second element will be ux into uy. The third element will be ux into uz, right? So the top. And similarly, you can write down the other element. Other than that, notice this is contributes only to the diagonal terms, because delta ij, so pressure will be there only in the diagonal terms. So ux plus p. Second point, uy plus p. This is the hydrostatic pressure, if you like, right? uh Yeah, so I think I have already discussed this in the previous class as well. I can just repeat it. Basically, when suppose there was an element, there was an object which was suspended in a fluid, half of it was outside and half of it is inside, and this suppose is the axis z equal to 0. Here z is negative and this z is positive. Um, and this was suspended. There is no flow, there is no u as a function of time. uh, U is not changing as a function of time. So in that case, essentially what you would have is, yeah, if you look at this equation, right? There's no space dependent in U, there is no time dependent in U, there's no flow for that matter. So U itself is 0. In that case, minus grad P plus F is going to be 0, right? So that's what we have written, minus grad P plus rho G uh, yeah, per unit volume equal to 0. And if you integrate, you will get P equal to, if you integrate this equation, you will get P equal to P0 minus rho GZ. And now, yeah. So just to keep an to sub the idea that, as you increase, I mean, if you increase the depth, going down, you are going to negative Z. So this comes with a minus sign, but if Z is negative, essentially pressure will increase as you go from the surface, which is P0, in the negative Z direction, because the Z is going to be negative, hence pressure is going to increase, right? So that's what it is written here, essentially. So pressure increases as one goes down in the negative Z direction, and the question is, what is the force acting on this element of the object? I mean, this could be some liquid as well, right? This could be liquid as well, or some object which is suspended in the fluid. The force per unit area which is acting is equal to minus grad P. And the total force acting on this surface, we have to take minus P, because it's acting inside, opposite to the normal, minus P integral over the area. But pressure itself is changing as a function of Z. Now, if you take this and put it, the surface integral, if you convert into a volume integral, you'll get a minus grad P, right? And grad P, if you take the gradient of this, you'll get rho G dV integral over V. And if we integrate over this volume which the surface was encompassing, then you essentially get rho GV. So basically the force acting on this element of area, which is shown in red, is equal to rho G into the volume of the liquid displaced, which is essentially Archimedes principle, right? Uh, yeah. So I'll also just continue with this. So basically, there is a vector identity U cross curl of U, and this is something like this, right? And U here stands for the velocity field, velocity of the fluid field. And if this is the expression for the Euler equation, incompressible flow, no viscosity, then this U dot grad U can be replaced using this particular vector identity. So you see here, you have U dot grad operating on U. So this you replace. So suppose you take it on the left hand side and this on the right hand side. So you see that this term is sitting here and this term is sitting here. And we like this because U dot U, right, and especially when multiplied by density, uh, so this will remind you something like the kinetic energy, right? Kinetic, because U square is a kinetic energy term. So basically the rho is inside here, inside the derivative, and so on and so forth, minus grad P. This is the force density. I have written it many times so that you don't forget it. You don't think it's the force, it's the force density per unit volume. We're working with rho. Now this is a cumbersome term at the moment, and we don't want to get avoid of it because we don't want to calculate curl of a curl. And the way to get rid of this term in this equation is to dot product this entire equation by U. So what I have done, dot product U dot the entire equation, And u dot curl of any quantity. So this this quantity is perpendicular to you because you've taken a curl. So this is perpendicular to you. And now you have taken a dot product with that with that vector. So obviously it's going to give 0, right? So this term is going to drop out. You're going to have u dot del t of rho u because you've taken dot product. You have taken a u dot. This was grad, remember? And then u grad p and f dot u, force density dot u. And this, now you have a u dot grad p, you have a u dot grad something, and this can be put together, u dot, and this in turn can be written as half rho u square. And now you see that it's quite nice because you can identify it with the kinetic energy density, right? And if it's incompressible flow, you can put the rho inside, and then again you can identify this with the kinetic energy density, and the pressure term sits here. And this phi stands for conservative. So one assumes if this force field is conservative, it can be, which means it can be written in terms of a minus grad phi. Phi I is the potential, is the interaction potential. Then you can write it this entire equation like this, right? So what it says is if there is a time dependence, if there's a time dependence, then that is related. So, so this equation, this is the kinetic energy density, and how does it change as a function of time, and that changes as u dot grad this quantity. And this quantity is has to be have energy units of energy density, because rho u square by 2, and pressure, remember pressure is forced by area, but multiply the numerator by L being the uh, with dimensions of L, and area also you multiply by L, so then it becomes energy per volume. So this is also energy density, and phi is of course potential energy, grad phi, so it's a potential energy density. So what you get is essentially delta T of kinetic energy density equal to, if you like, uh, yeah, so you get u dot grad of this. Now for steady flow, what is steady flow? U is not changing as a function of time, thereby kinetic energy density is not changing as a function of time. So for steady flow, this term is going to be 0, and for steady flow in that case, you have u dot grad h equal to 0. Now u is not 0, so grad h has to be equal to 0, and so right, so grad h has to be equal to 0, and moreover, so this defines essentially the streamline, right? Because basically along so you're taking u dot, you're taking the tangent, if you like, uh, basically locally in the direction of flow, but grad h is to be equal to 0, but each of these terms are not equal to 0, which means that because there's a finite u definitely, right? And you will have a finite pressure, which means that along that line, there's no change in the value of h. So if only if you have a steady flow, you can have the kinetic energy density plus pressure, which is the energy per unit volume, and it could have kinetic component plus interaction component. So if you have water in the ocean and force acts on it, gravity acts on it, the pressure increases as you go down as rho gh. Plus, if there is some other potential like static electric potential or whatever, that equal to constant along the streamline of a steady flow. So that's the essential message, uh, right? Yeah. Um, yeah. And how does one use that? So this is basically the Bernoulli equation for an inviscid fluid, the kinetic energy density plus pressure plus phi. And suppose you had a flow, um, right, with a larger cross section here and a smaller cross section here. And suppose there was no scalar potential like this, then you could write rho u1 square. And if if there is a certain flow velocity, u1 uniform velocity along this flow, suppose. And why uniform? Because if you had viscosity, the velocity will be zero at the walls. But if you have inviscid flows, you will have finite velocity at the walls, right? Because it will slip. There's no viscosity, there's no dissipation. So if you were in this limit, or you were far away from the, if you're talking about, so as we'll discuss in the next module, so basically such flows can be there as long as you're very far away from the boundaries. Uh, so if the condition of Euler flow was satisfied, if you're looking at flows which satisfy the conditions of Euler flows, right? So in real viscous flows, there would be, yeah, the profile would be different. But suppose you had Euler flow, uh, then you could write rho u1 square, the kinetic energy density here, plus p1, the pressure here, equal to, this is a narrow constriction, and you're assuming that there is no density change. So the same amount of mass of fluid has to flow through a narrower constriction here. So if the amount of mass has to be the same flowing here because there's no density change, then the velocity here has to be higher. Yes, because flow of water, so because flow of liquid will be rho into u1, rho is fixed, u1 into a1, right? That's the amount of mass which will flow per unit time. You do u2 into a2. In addition, this relation will hold of Bernoulli. Now you substitute u2 from this equation, right? And that's all that we have done here. And then we can write down the pressure, and we can write down the pressure difference in terms of u1, a1, and a2, right? And a1 was a positive quantity. A1 was a positive quantity. So sorry, a1 is a positive quantity, and so a1 is larger than a2. So this ratio is larger than 1. So this is a positive quantity. So the pressure here is higher than the pressure here. Now note, we are talking this about the hydrostatic pressure. So there was some kinetic energy density plus some pressure. Here the kinetic energy density has increased. So the internal energy, so energy per unit volume, the internal energy of motion of the molecules has been converted into some kinetic energy, increased kinetic energy density. So hence P1 has decreased to P2 to maintain this equality. So I want you to remember that. By the way, we were talking, so in this slide, we were talking about PV equal to nRT, and even if it was not an ideal gas, there would be another equation of state. And we said that this is incompressible. Uh, but here we are talking about changing pressure. So is there any contradiction? I just want to highlight this point. Hence, this point was not highlighted in the previous recording. So what I'm saying is one can have incompressible flows of compressible fluids. So the flow is incompressible. The fluid can be compressible, but if you are at low Mach number and over the scale of the flow there is no change in the density, then you can have incompressible flows where divergence u equal to 0. So here pressure is changing, but the pressure is changes such that there's no effective change in density, or the change in density is negligible, right? So you're going to have that the pressure has decreased, the internal energy density has been converted to kinetic energy density, but the density has not changed. The flow profile, the flow u as a function of x, y, z, as such that a divergence u is always equal to 0. So that is being satisfied. So one can have incompressible flows of compressible fluids. Uh, the last thing I want to discuss for the next 10 minutes is a certain quantity called vorticity, and that will set up the flow. That will set up the required discussion for the next class. So, as I showed you that del u x, del u y. So, if you had a pure shear flow, that can be not a pure shear flow. Sorry, I just mean suppose you had two walls. One wall was static, this wall was moving. So if this is the x direction, then the velocity in the x direction is changing as a function of y. Suppose this is y and this wall is static, so hence the velocity of the fluid del u x will change as a function of y, and that can be written down into a symmetric matrix, and this basically describes pure stretching and shearing, and an antisymmetric tensor, and this is essentially like the curl of u. So this part especially is the curl of u, right? Now note these lines of flow were perfectly straight, and yet that shear can be broken up into a part which has a curl of u. So there is a rotation of the fluid, though it is not visible as per the streamlines, right? So I want you to notice that. This is pure stretching and shearing, but this has a rotational component as well, because we have all that we have done is algebra. And the tangent of omega are called vertex lines, and omega measures the amount of swirl, the amount of rotation in the fluid flow. So even with straight lines, it can be decomposed into a pure stretching, pure deformation, plus a pure rotational flow. Now, we want to discuss a bit more about the meaning of vorticity. Vorticity can be calculated, the vorticity vector at any point in the fluid where there is a flow, and flow has to be a function of x, y, z. If the curl of u exists at that point, then the vorticity vector is, you have a finite vorticity at that point. So omega at r1 must mean that omega is not equal to 0. If you, even if you take a small line element, a complete circular line element, for calculating the curl, curl of u can be written as u dot dl integral uh, a closed loop. So at each point in space, if you draw a closed loop, um, omega should come out to be non-zero at each point in space, and it's not about just pointing around the origin. So I want to show you also that you can have flows of velocity vector fields where u is changing as a function of x, y, and z, so that the velocity field or the streamline looks curved. So it can look curved but not have vorticity. An example of that is u bar equal to alpha. Alpha is some constant, and later we can take it to also to be a function of x, y, z, as we will do soon. Is equal to minus xi plus yj. And if you take the divergence of u, you'll see that it's an incompressible flow. Divergence is equal to 0. Moreover, if you take the del ui del xj, right, you'll get minus 1 plus 1. The volume element is, so the trace is 0. There's no volume change in a finite due to the flow. Moreover, curl of u equal to 0. So how does this flow look? It is the familiar one, which is corresponds to pure stretching flow. So this, if you see, will have This, if you see, will have so let's try to visualize this. So as you increase in the x direction, the flow field, the velocity field, the value of the velocity increases, but in the negative direction. The magnitude increases, it's in the negative direction, right? If you go along y, the velocity field, the value of the velocity at different points in space, it increases. If you are here, you both have a minus, if you have a y velocity as well as a high value of the x component of the velocity. And similarly, so on and so forth. You can reconstruct that. If you were in the negative x direction, it means that it has a high velocity in the x direction, because ux equal to minus x. It increases as you go, but it moves in the positive direction. This is the flow field. You can just think a bit, and so on and so forth. So here you see curved, you see curvature, right? You see that the flow is bending, if you like, but vorticity is equal to 0. On the other hand, if you had a velocity field which is minus y x 0, and this is some constant at the moment, right? And if you take the curl, you'll get a finite value of 2 alpha. And I want to show you that this is uh, what this flow field is. So basically what you have is, as you go along the x direction, ux, as you go along the x direction, um, so basically the x component of u has so the x, as you go ux, sorry, as you go along x at different values of x, yeah, sorry, you have, this is uy actually, right? And that increases as you go in the x direction. So uy, the value of uy at this point is high. But here ux is 0. This is purely in the y direction. That's what it says here, right? The uy, you have a finite value, and that depends upon the value of x. X, higher value of y component of the velocity. But if you are the on this line where y is equal to 0, you don't have any x component of the velocity. And similarly, you can think how it is going to change as you go along this direction. So this direction, x is equal to 0. So you don't have any y component of the velocity, but you have an x component of the velocity, right? So here the ux is high, ux equal to minus y. Uh, Yeah. So y is negative, hence it's moving in the positive direction. So this is the circular flow, and it has a curl. It has a curl, and this is directly taken from David Tong, chapter 1, fluid mechanics, right? But what I want to impress upon you, that even if it is going perfectly circular around and shows, it looks to have a circular pattern. Um, there can be cases where the vorticity is equal to 0. And just to give an example of that, that suppose this alpha was such that it was dependent upon r. Suppose it was dependent upon r, and what I have written here is just the curl of any vector in suppose spherical coordinates. So you have, for the r hat, you have a derivative with respect to theta, with respect to phi. For in the theta hat direction, you have a derivative with respect to phi and r. And again, in the phi direction, you have a derivative with respect to r and theta. And I want to impress upon you that this vector, this vector field, would look, and this is a function, this is r dependent, this minus yx, essentially you see that it is always pointing in the theta direction, So it would have a finite theta component, and the magnitude will be x square plus y square equal to r, right? So it would have a term like this. So this would be uh yeah. So that's the field. And if you want to do it mathematically, then you can refer to this. It will tell you how to convert, how to go from uh xyz Cartesian coordinates to spherical coordinate system. And so if this is the vector, so if you are written in the spherical polar coordinates, it will look like a function of r, no component in the r direction, a component proportional to r in the theta direction, and again this is 0. And if you take a curl, only this term will survive. And so you have this r sitting here, you have this r coming from a theta, so this is a theta if you like, this is a r, this is a theta. And so instead of, so we have written that r, but if fr was such that it went down as 1 by r square, so fr had a 1 by r square dependent, then in spite having the streamline which look like this, which is clearly circular and appears to have vorticity, the vorticity will be 0, right? So I want you to notice that that just curved lines don't indicate vorticity. You actually have to calculate curl to figure it out. The other physical picture which I want you to have is just turning or rotational looking velocity vectors do not imply non-zero vorticity, as I just discussed in the previous slide. So here you have two different velocity fields, of which have circular streamlines, but in this it would correspond. So suppose if r was going as 1 by r square, then you would essentially have, suppose you had a paper boat, then as it goes around this point, and this point is a singular point, uh, this paper boat, which suppose is shaped like a cross, this is not going to rotate. It will have only finite, the velocity field will only have finite velocity if you take a small, what is it called, line element, closed loop at any point, and you calculate u dot dr on the loop, and it will have a non-zero value. The consequence of that is, if there is some very light cross which is drawn in a velocity field which not only goes around the center, and here you have a singular point, but it also rotates. Here you see it's rotating as it is going around a bigger loop. So this itself is rotating. The fluid velocity field is rotating, and it will carry this light, whatever paper boat on it. So this has vorticity. This does not have vorticity. So that's the thing which I want to impress upon you. The other reason we discuss vorticity, vorticity can be an entire chapter, and vorticity is also extremely important for turbulence. But here I'm just giving a quick introduction which will set up the next chapter. So what I want to say, that if you know the vorticity field omega r, and in some cases you might know the vorticity field, you can calculate u of r, the velocity field. And how and why is that? So for that, we will take the help of the knowledge that we already have from electrostatics. So incompressible flow, so divergence, so here you have, for incompressible flow, divergence u are equal to 0. In electrostatics, um, or electromagnetic theory, you would have divergence of B equal to 0 for a static current. So we are looking at static current, and you have curl of B equal to mu 0 J. And then if U was analogous to B, we're just doing a mapping, then curl of B equal to omega R, right? Now, now, now you know that B can be written as a curl of A, and in that case, U can also be written as a curl of A. right? And so basically, if this is non-zero, if this was non-zero from this experience, so you will have, you can take curl of A equal to 0 j. This comes like this, and here it would come something like this. So making this mapping just like A field can be written as mu 0 by 2 pi, a static current density integral over the entire volume x minus x prime. You can calculate an A, and from that take the double. Uh, you can take the double derivatives, right? To calculate the vorticity, you can calculate velocity field and vorticity. You can similarly write AF fluid equal to omega r dash, assuming that you know vorticity. Yeah, so here we have just done some identical algebraic manipulation. You can you can calculate this. This will be a field, and you can also calculate directly the velocity field. So if you knew so if you know vorticity, the velocity field can be written just in analog to the B field in terms of omega at each point in space dot cross r dash, right? At any point, you have a certain vorticity vector cross r dash into dv dash r minus r dash whole square. Thus, just in analog with this. So if you know vorticity, you can calculate the velocity field as a function of x, y, and z. However, there are certain differences. So basically, what the differences are, that you can calculate this even if this omega is a function of if omega was changing as a function of time. So even if it was changing as a function of time, we could calculate velocity field, time dependent velocity field from omega, whereas this relationship holds here only for static problem, because remember curl of B equal to mu 0 j plus mu 0 epsilon 0 del E del T. So if there was some flow, if there was some change, right, there will be other time dependent. So this holds for a static problem, whereas this holds for a dynamic problem. Moreover, uh, suppose you didn't have a curl. Suppose vorticity was 0, then V2 can be written as plus or minus grad phi, right? You can basically write the velocity field in terms of a grad phi, because curl, if you take the curl of this velocity field, curl of grad is always 0, right? So whenever there is no vorticity, you can write V2. Whenever vorticity is 0, you can have uh, V2 can be written in terms of curl phi. On the other hand, suppose we are calculating a velocity field from the curl, and yeah, so then your velocity field is actually ill-defined up to a term. So if there are certain terms where velocity field, uh, so so if you're calculating curl, so from the you're calculating your velocity field using this expression from the curl, you could, in addition, due to presence of boundary conditions or whatever, you could have some component of the velocity field which is coming from a minus grad of phi, and that if you took the curl, it would contribute to 0. So velocity field will still be ill defined or not perfectly defined up to this such a term, right? So you can calculate the velocity field, but if there was a certain part of the flow which comes from grad phi or minus grad phi, where phi here is not electrostatic, it's not electrostatic, it's not a potential, it's not a conservative potential. Just 2 minutes I will require, I'll finish this. uh, then that won't show up in omega, and that is not going to contribute. So I already pointed out that by Seibert's law, the B field holds only for static currents. Uh, and if there's a time dependence, that B field, I mean, it propagates with a time of CT, whereas this B is defined, I mean, omega is defined instantaneously, and even for time dependent cases. So omega and u, they are defined instantaneously in terms of time, right? There's no time dependence of v involved. So if you had a current change, then that will be felt at a distance greater than ct after some point. So if there's a current change here, the B field will take some time to travel at very large distances, and that B field will change after some point in time. But on the other hand, here at every point in space, if you have a you are defined, and if there's a velocity to that field, instantaneously you can define a vorticity. And if vorticity changes at some point, or the, I mean, so here if current changes, then B change will happen after some more point in time. But here if omega changes at some point in space and time, velocity field change will be instantaneous. So there are some these differences, and these are actually pointed out very well. So these points are taken, I think, I don't know why there's a third point. I think some point I took also from physical hydrodynamics, um, right? And this is there in page 25, Tong chapter 1. So the last point which I want to do is basically you saw this equation and this term was replaced. So this term using this vector identity was replaced by a combination of these two terms. So I have exactly copied it from the previous slide. In the past, we did a dot product of this entire equation with u dot to drop this term. But now we want the curl of u. We are not dropping that term because we want to write down the same velocity in field equation in terms of vorticity equation. So hence we are keeping this term intact and instead taking a curl of this entire equation. Previously we had done a dot product with respect to u. We want to write this equation in terms of curl of u, which is vorticity. Hence, we are taking a curl, and a consequence of taking a curl is this term, because this is grad of u of a scalar quantity kinetic energy density. So that is going to drop off. Uh, Curl, it can go in, and this will give again vorticity. This already is giving uh, basically mm, so u cross so curl of u gives omega. You already had a curl, not it. Okay, u cross. Okay, you had a u cross omega. Now you're taking the curl of that. Sure, these terms will drop out, and what you will have is an equation which is like this, right? So, so this is the vorticity equation, if you like. Under certain conditions, you might be able to calculate that. And next, using another vector identity and using divergence u equal to 0, um, divergence of omega, vorticity equal to 0, one can write down in terms of total derivative. This was partial derivative, this is total derivative. You can just work it out, do the algebra. It can be written as d omega dt equal to omega dot grad of u. Now this equation says that if there was a vorticity in the field, it would be stressed. It would be, so this is going to act and change u, and there would be a change in vorticity as a function of time. But if vorticity at a certain point of time was zero in the Euler equation in incompressible fluid, then there can be no change in the vorticity, because you have to do a dot product, and if it was zero at any instant in time under the conditions that we are discussing, under Euler flow, incompressible flow, it already had vorticity. Yes, that can evolve and increase and decrease and do whatever it wants. But if vorticity was zero at a certain point of time, it will continue to remain zero. So this is the primary result I wanted to say, and this will set up discussion for the, so, or there was some part of the velocity field whose velocity will zero, that is not going to later contribute to the vorticity flow with respect to, the discussion that we were having, that if you calculate velocity fields from the vorticity, you could have a component which is ill defined. You don't get, you only get part of the velocity field which had vorticity. You can still have a velocity field which is coming from grad phi. Okay, so this is where I end, and yeah. So I have already told that, if you have this term, it can have a vorticity. It has a vorticity term as well. Yeah. So that's enough.